All right, welcome to another live stream um, where we are doing some ray tracing in our D3D11 renderer, where we try to create a water effect. So first, let's see where we left off last time. So last time we built this bounding volume hierarchy to do fast ray tracing on a 3D mesh, as you can see right here. We got a frame time of around 2.5 milliseconds for this view, which is not too bad, but also not good enough yet. Since this is only like a small mesh taking up a small part of the screen, not full screen or anything yet. Uh, we can probably do a lot better, but I also want to add some more features. So we can move the model around, which would help. So here's the to-do list. I first want to create a little visualizer for debugging the BVH so that we can sort of look at the differences when we implement the so-called surface area heuristic. I also want to add some GPU performance counters so we can use something better than the frame time to really see what's going on performance-wise. I want to add a heat map so we can we can really see the quality of our BVH. What the heat map is going to do is basically show green for rays that didn't have to test with a lot of ABBs, and show red for rays that had to test a lot of ABBs. And as the quality of the BVH gets better, there should be less red spots. Then we'll add a little fixed location for the camera. Then we'll improve our BVH using surface area heuristic. Let's see, I probably want to do this first, where we can move around the model before we start optimizing it more. I might also want to do a ray tracing debugging shader first. But yeah, just to go over these, right now what we do in our traversal, which is not very efficient. Let me get the traversal code. Yeah, right here. Basically, we load, when we're on a node, we load that node, and then we also have to load the children. But we don't really care about most of the data in the children. We just care about their bounding boxes. So instead of loading the children, we can store the bounding boxes in the BVH node. We also don't care about the node's bounding box itself, since we're just testing, should we go left, should we go right. We also don't care about the box of the node itself in the leaf node case, since we already know that we intersected with it in order to even hit this case. The only downside will be this first check, which we'll need to change. But we can just simply add one extra ABV to test if we even hit the BVH. And once we add a mesh instance BVH, we basically have a BVH of BVHs. Sounds a bit complicated. But what you basically do is that like you have the world BVH, and you check which models am I even hitting. And then if you hit a model, you traverse that model's BVH to see what triangle you hit. Yeah, so that will need to change. But doing this will be far more efficient. And then I also want to test having 2 children, 4 children, or 8 children. Because traversing a node is expensive, and once we're in the node and we are testing, like we're testing the ABVs, it should not be too bad. Yeah, and also want to add some extra debugging stuff, so we can have we can just see what the camera sees. Like we're just ray tracing our camera view. And then I want to add some more features do barycenter coordinates for UV mapping and normal interpolation. So you can actually also do the shading on everything. Alright, so let's get started with the BVH visualizer. What I basically want to do is the following. In my main file, if I can find it, I want to add a new slider. Label BVH depth. I'll create a debug value in a second. So minimum is going to be actually -1. -1 will just traverse the BVH as if we're not debugging. And if it's any other value, we'll use that. And I think the maximum depth we said was 16. Let me double check that in our BVH building code. Yeah, maximum depth is 16, so it should never go beyond 16. The depth will get lower if we start having more children per node. Let me copy this. Let's add this to our Unity build file. And these are just here. Oh, I misspelled global. These are just here for debugging. We're gonna throw these away eventually, so I don't really care about having globals here. Yeah, spell it right that time. Cool, then we can copy this, go to our rendering thing, and in our constant buffer, instead of having 3 floats of padding, we can add an integer, debug depth. Let's find where we fill that thing. Index buffer. Yeah, right here. Debug depth is going to be the global. And then we need to reflect that change in our shader, because those structures always need to be in sync. Let's make sure our vertex shader also matches this. Perfect. And then we can now access it in our ray tracer. So what I want to do is basically just check this value. If it's -1, we will just do our regular thing. If it's not -1, we will do our debugging thing. And basically, I'll just call this hit. I'll just bool hit. Hey, Cookie says hello, and former Canuck waves. Hello. We don't even need to pass the value since it's a global, because it's in our constant buffer. So let's use the famous copy pasting technique to implement this function. So you copy, copy, and paste. And first of all, we can simply check that all the return -1s will be returned false. If, what do I call the variable again? I always forget how I call my variables. I even misspelled it, it should be debug. Let me fix that. Debug BVH depth, awesome. Let me fix that right here. Awesome. yeah, I'm just gonna check if this is 0. It means we passed our test here. So either it's false or true. And if it's some other value, then we will actually traverse a bit more. And I'll have to add a second stack. I want to add a depth stack. And I'll also add a current depth, which is 1 at this point. Right. So when we put things on the stack, here's a traversal. We need to first put our new depth. Current depth plus 1 on the stack. And I'll do the same here. And if we traverse a new thing, we'll say current depth equals current depth plus 1. And the same goes here. Same goes here. And here we'll also need to make sure we pop this value. I actually made a mistake. I was using stack instead of depth stack for depth. That is not good. It should be that. Yeah, I'm going to use this order. And then I also want to what do we want to do in case of the leave nodes? I think we either return true or false if we hit the leave, or we just do nothing. I've actually never done a debugging view like this, but it should be really nice for debugging. Let's definitely not intersect triangles because we don't care about triangles. And here we want to pop the depth. So what I'm thinking is, when we traverse a node, we want to check the depth, because if we traverse it, we hit it, right? So our first node is actually the first one, so it would be 0. I'll just check if current depth equals whatever our debugging value is. We'll return true because we hit it. And right here, I'll just return false, and we'll just test what that looks like for now. Yeah, so we're not keeping track of depth in here, and we're checking for certain depths where we just stop. Let's try this. Undeclared identifier array. Oh, this should be called array, and this should be out t. We don't even care about the t value, so let's even get rid of that. It's still in there. It is still in there. Yeah, that's our regular intersection. Cool, so let's try this. Wait, first, if hit refl color equals 1. Another error. Oh, yeah, we need to get rid of T. Reference color is, oh, I need to move this out of here. There are so many warnings in here. I should probably fix this up at some point as well. So right now it's 0, and if it's -1, we should be, yeah, we're out of debugging mode, in debugging mode, level 0, level 1, level 2, level 3, level 4. And we can see it get more and more precise as we go down levels. Just with those last 2 levels, suddenly becomes black. So I think what we might want to do is return. Oh, right, because there's just no ABBs on that level. That's fine. Is there a way we can color these a bit better? Perhaps based on the node index, we can give them colors. Would that work? I don't know. Let's keep it like this for now. So that's actually first thing done really quickly. Now I want to see if I can get a GPU performance counter. So let's Google if that's even a thing in D3D11. So I know it's a thing in D3D12. D3D11 counter. This sounds awesome. Define a counter that's dependent on hardware info. Counter disk. Create counter, check counter. Counter type. Huh. Oh, perhaps if we create counter, we get some sort of counter object. Yeah, we get a counter object and then we can probably check that. Can we? This is the derived class of asynchronous. Begin commands and end commands. Right. So what I think happens is basically with these commands, these will put a command in the command buffer for the begin and end of the counter. And calling this get data will sync the GPU. So we should call get data after we present to get our data. Let's try it. That's actually, yeah, we'll stick it in a global and we'll render it with imgui so we can see the last frames counter. So like that, and when we initialize our stuff, not that one. This one. We'll just put that at the bottom. Yeah, right here. Create counter, awesome. Well, let's stick this in its own scope so we don't get a bunch of variables that have the same names. Let's look up what we put in the structure. Is a D3D11 counter. Well, there's only one type, so let's use that. MISC flags. Let's look this up. Reserved, so it doesn't do anything yet. So we can just leave that at 0. Oh, yeah, like that. Cool. So that fails to crash. Let's see if we crash. We crash, so that's definitely incorrect. Let's see, do we have any debug information? Invalid arguments. It's out of range. The device independent counter value, this value was out of range. Is that the same value? Probably. Yeah, so this is out of range, so perhaps counter should just be 0? What should it be? Device dependent. Define a performance counter that's dependent on the hardware device. Independent hardware vendors may define their own set of performance counters for their devices by giving the enumeration value a number that is greater than the value of... Oh, so should I just do +1? And then I need to cast that to a counter. Perhaps this has some hardware specific trickery going on. So we might need to look it up on AMD's website. Yeah, it still doesn't like that. Let's look this up on for AMD. Oh, I opened that in the window. Device dependent counter value was out of range in D3D11. I'm not sure how we can get these counters. Let's try the value 0. Because I would really hate it if we had to rely on frame time. Now it just gives us some error without really telling us what. Is even an error. Yeah, it's still invalid arguments. But it doesn't say what the invalid argument is anymore. What happens if you use 1? Like, I doubt that constant is like the maximum number or something. That would be even stranger. Why is it that value though? What if we do like +2? This is a really confusing API. No. For a list of counter types. Find a performance counter that's dependent on the hardware device. Counter info. Ah, we can just get information about the counters. Perfect. Check counter info. Oh, semicolon. Let's just see what this gives us. Perhaps it will tell us that there are no counters available, none at all. That would be terrible. Num simultaneous counters 0. What does that mean? Number of counters that can be simultaneously supported. Perhaps we just don't have any counters on this hardware. Perhaps query object, perhaps we can use that. Query timestamp and query timestamp just disjoint. You will need one timestamp query for each stage of your render that you want to profile. In my case, one each for shadow clear, shadow objects main clear. Right. Yeah, this is perfect. Let's try this. So let's throw this away. Create query. Let's see what data we need to give it. Some query. Well, that's a query type, and we can just use the timestamp. And then misc flags, which is probably also just reserved. Yeah, this also seems to work the exact same way. How strange. Um, this kind of query is only useful if two timestamp queries are done in the middle of a query timestamp disjoint query. The difference of two timestamps can be used to determine how many ticks have elapsed, and the query timestamp disjoint query will determine if the difference is a reliable value or has a value that shows how to convert the number of ticks to seconds. Right. So we also need to create this disjoint. Yeah, let's do that. Let's just crash if that fails. Predicate hint. I'm not sure what that is. We'll look that up in a second. Oh, I'm making lots of mistakes here. Awesome. And this one's not going to be disjoint, that's just going to be the regular query for the water. Let's look up that miscellaneous flag. Tell the hardware that if it is not yet sure if something is hidden or not to draw it anyway. This is only used with an occlusion predicate. Predication data cannot be returned to your application value. Okay. Looks like we do not need this, so we'll just leave that alone. Let's create these variables and get rid of that old one. So if I understand correctly, well, let's first test if this even works for wasting time. Yeah, alright, this works. Cool. So if I understand this correctly, we can just go to a render function. Basically take this whole chunk. But I don't even care about the state changes. I just care about this draw. And I can just do a context, begin. And then say D3D11 this joint query. Oh, without the pointer, the dereference. Then begin the regular query. Then do the same the other way around. And then somewhere after present, we can get the perf data. So I'll just create a new function for that. Let's return it in milliseconds as a float. That should be accurate enough. Does it just get data? Figuring out this stuff is always so annoying. Oh, context get data. That makes sense. Right. Get data size. Oh, I pressed the insert button. Never press the insert button. I can just do a size off. I don't need to do count off. Then do that with the regular data. Oh. They put that insert button just to troll the user. Yes. It is the troll button. I don't know of anyone who actually uses that button effectively. Like, it's so weird. I don't see any reason to use it. Like, I can imagine it being slightly more efficient somehow, but it's so awkward to use. Get data flags. More flags. Don't flush. Yeah, we do want to flush though, so we'll just pass 0. If we don't flush, we won't get any good data. Well, although, because we do this after present, we don't have to flush, I think. How would this create an infinite loop though? I'm not sure. Oh, it's continually called. Um, yeah, so you keep calling it until OK. Yeah. We could pass that flag to optimize, but we just want to get some, we just care about how long it took on the GPU. We don't really care about how long it took on the CPU. Well, we don't care about it syncing really. You tried this use insert key? Yeah. No good use for it. Yeah, not when you have that handy delete key right next to it. Exactly. Like it only if you're going like for as little button presses or some as possible or something. I don't know. I never have that thing where like, oh, I have this one piece of text, but I want to write this other piece of text that's the exact length over it. Like when does that happen? So I have no clue what data this is returning. Perhaps it says it on the type that we passed. Why is this so convoluted? Oh no. Oh, it returns the UN64. Return a this. Oh, that is so much more useful. Cool. So instead of doing this crap, we can just do this. And for the other thing, we can just do this. Oops, deleted the whole file there. That actually happens too often. Imagine with cache values. Yeah, like you're in Excel or something. But even then, like you select a cell, you just type the new number. Perfect. So we can now do the following. If disjoint data dot disjoint, then that means it's bad, right? Yes, something occurred that caused the timestamp counter to just be bad. So we'll just return some bad value that's -1. So we don't know how long it took. Otherwise, we can do some mathemagic. That's hertz, so we'll want to convert that so we get either milliseconds or microseconds. I think milliseconds are good enough. I actually already called the function in milliseconds, so we'll just do milliseconds. So we need to divide this by 1000. I'll actually convert this all to doubles for the calculation. I never use doubles except for this stuff, where I just like now I really care about my precision. So once you understand this API, it's actually not too bad. It's just really convoluted to initialize all this stuff if you don't know how it works. But it's nice that it will tell you like, yeah, we got some valid data or we did not. And that you can actually calculate the value in time instead of just some arbitrary cycles. Cool. So let's add this function to our graphics interface. This is also just a debugging interface, really. Like, I wouldn't want to ship a game where the graphics interface was this. This is just, oh, I need a function. Let's add it. And let's link that after we initialize all our stuff. Again, insert. Is there a way to disable that key? That would be perfect. Cool. And what I'll just do is I'll create a variable here. Last time order for last order per time. I will set it to that invalid value of -1. And after we present, we'll call that function and assign this variable, and we'll also always just do mGUI text order render time in milliseconds. And we'll put that right there. Yeah, right there. Right there, not halfway through a function call. Let's test if this works or not. Well, looks like we are spending a lot of time on ray tracing. That does not seem correct. Let's see what's going wrong. So we do our begin and end calls. Yeah, those return voids, so there's no error checking here to be done. And here why do I keep why do I keep losing track of my functions? Let's just debug this. So this one is okay, and we got the following. It's not disjoint. Frequency is 25 million, whatever that means. So the clock is at 25 megahertz. And we get some really large number here. Yeah, so we need to divide by that for milliseconds. But we get some ridiculously high number. That definitely seems wrong. Let's initialize this to 0. Try this again. Because perhaps it's not even writing that data. Yeah, now it's 0, you see? So it says okay, but it didn't actually write any data. Well, it did write data. Huh? Then why is the value now 0? Oh, the minimization bug. Oh, so now it's 0 again. I'm confused. Let's double check what it should be giving us for a timestamp. Returns to you in 64. When using this type of query, device context begin is disabled. So perhaps we're using it wrong? This kind of queries only useful if 2 timestamp queries are done in the middle of a... Yeah, the difference of 2 timestamps can be used to determine how many ticks have elapsed. When using this type of query, begin is disabled. Perhaps this article will tell us. Ah, so we just use the end query. And we need a begin frame. Ah. So instead of calculating a difference like our disjoint, we just put a timestamp there. We need to calculate how long things took to reach that point. So we're basically placing a marker here and placing a marker here. So this won't do anything. And we'll need some new counter. So new query that will just say start counter query, which will be an end. So this is actually not related to our water anymore, it's just this timestamp. And I'll call this water query. I think that's a bit better naming. Yeah, we can do this, and we can actually use this, reuse this description for this other counter. Like that. Yeah, so we query, reload that thing. So we'll do this. And this is just going to be 8 bytes. Okay, U64 is not going to change. Um, so we'll say time diff. Like that. And we can convert that to milliseconds. Zero milliseconds. Doesn't seem to work. Perhaps this doesn't work after presenting, it clears the counters? Just guessing now. Now it's -1. Oh, because it can't read. We got a disjoint if it's -1. So this returned false, which is apparently not failing. Let's just return different values if they're false. So this is actually not an H result. This is, oh, this is an H result. I thought it was a bool for a second. So we'll make it -1, -2, -3. 2, 3, 4. I can actually test for this joint right there. Semicolon. Oops. Right, -2, so that first call is always failing. So what if we move this after represent? -3. So then this one fails. Huh. So here just loops and waits. I should have just been reading this article from the start, really. um, simple. We'll explain the basics. The truth is that to do proper GPU profiling, you need to double buffer your queries. Yeah. 2 copies of everything. This is because the CPU and GPU run simultaneously, not sequentially, or at least they should for efficiency. While the GPU is rendering frame n, the CPU is forging ahead and working on frame n plus 1. When the GPU finishes frame n, it puts it up on screen, starts on frame n plus 1. Yeah, that builds. Okay. So I want to add this little waiting code, which is just this while this equals as false, wheels is sleep 1, which will give other threads opportunity to run. And then I want to try run this here again before we present. And this timestamp should work even though it would stall our pipeline. It should work without the double buffering. Okay. Oh, it's being used without being initialized, right? Don't need this anymore. So it hits true at some point, which is good. Still the -3. So should I also be while looping the other ones? Because if that one is done, the other one should be done as well. That makes no sense to me. Also here, there's no looping. This is really annoying. Let me double check that I actually start these. Yeah, I end. My music stopped playing. I should start some more music. Let's listen to this album. What an annoying bug. To do proper GPU profiling, but do you need it? Yeah, I think we need the double buffering. Yeah, let's just implement that. We need 2 of these, and 2 of these, and 2 of these. When we initialize, we need 2 of all of those as well. Just 2. I don't think you can really triple buffer in DirectX 11 anyway. Can also get the frame index from the swap chain. last percent count. Is that what the function that I'm looking for? Or is that only in DirectX 12 a thing? The number of calls. Gets the number of times that present or present1 has been called. Yeah, probably not what I'm looking for. Although I'm saying that right now, however, I can say double buffer index, which will be 0 by default because we zeroed that whole block of memory. But I'll zero that value just in case. Just in case I decide later on I don't want to zero that block of memory. So I think this is where the swap chain gets created. Yes, swap chain, create swap chain. The buffer index 0. We'll just say swap chain. Get last percent count modulo 2. Oh, that needs to be outputted as some value. Oh, just the uint. And this is actually just this. Cool. And then we just copy paste this. To our present call. Right there, and right after we call present, we'll just update that buffer, that value. And then for all our counters, we can use that index. And that should solve all our problems that we are having. Like that, and that, and that. Yeah, Microsoft's documentation is not great on this. Usually their documentation is actually pretty okay. Will you work? It still doesn't work. Ah, what is going wrong? We'll be waiting for us. Times inquiry will send back a 64 retaining. Yeah, now we definitely want to call this before present, otherwise our value is otherwise we're reading the wrong counters. Pretty okay, that's high praise. Yeah. Like documentation that's pretty okay is already pretty good for documentation usually. Sometimes there's documentation where you'd wish there was no documentation. Okay, just as a sanity check, am I initializing these correctly? It seems that I am. Yeah, we didn't care about the predicate hints. I looked at the docs, now I'm more confused. Yes, in that case. Or even worse, if the documentation is wrong. That is the worst thing to happen. Wrong documentation is worse than no documentation. This is so annoying. I just want these counters to work. I just want some performance data. Oh, why is this so difficult? Yeah, so this is for syncing, occlusion, what else is there? Pipeline statistics. Uh, I'm already running out of water. Perhaps I should just give up on this for now, do something else and come back to it later. So I don't want to be spending hours on just doing stupid performance counter. And just to make sure, even though it's returning false, it's actually not writing to this value, right? Yeah, it's not giving us any useful data. Even though this works fine. He ends things after the percent. Oh, that's probably for... That's to get the whole frame time. Should we be doing that as well? So I also need to use the last index, which is annoying. I don't know. Like, if this is done, these should also be done. Yeah, I don't want to be spending a lot of time on this, so I'll just leave them like this. I'll actually add a, should I add like a define to disable them? Because they seem to be eating a lot into the frame time right now. Yeah, let's I'll just see where this where this fails to compile and fix it there. And then just initialization codes, yeah. Yeah, let's do something that's a bit more fun than this. Yeah, cool. Let's see if that actually made a difference or if it's just the recording that's making it slow. Yeah, that actually makes a difference, see. We're back to our 2. No, it's 3.3 milliseconds again. Okay, perhaps it's just the stream that's slowing it down. Maybe I won't really be able to do really good performance testing while live streaming. So I'll have to figure something out for that. I'm just gonna put a dash here. We did some of the work, but we didn't finish it. We can do a heat map. Or we can just do something fun like surface area heuristic. I'm feeling like doing something fun. Yeah. I'm gonna get some water first, and then we'll implement the surface area heuristic because that's more fun than adding more debugging things. Right, I'll be back in a like a minute. All right, let's do some fun. Let's implement the surface area heuristic. Just rolls of the tongue. So to explain surface area heuristic really quickly, when we were talking about the BVH, um, we basically have our triangles, which Venn triangles be overlapping like that. And we need to draw boxes around them. What we're doing right now is just taking the longest axis and like splitting it in half, which would actually look a bit different because they'll always encompass full triangles. So it usually looks a bit like this. But sometimes the middle split is not the best. So when would that not be the case? Let me just delete this real quick. Just to give like an over-exaggerated example, we could have a mesh that would roughly have data that's a bit like this. Not even like this, no, let's change it a bit more. What if, yeah, like this, like this, like this, and then we have like a bunch of small triangles here. So basically our triangles are not laid out very uniformly. So what we would do currently with the median split is we would go, you know what? The center is about here. Let's split there, and let's split there. But now we have a box with 3 triangles, and that box would actually be this size, with 3 triangles, and we have a box with like a lot of triangles. That is not the most efficient way to go about this. What we would rather do is do this. Basically, how would I explain this best? Oh, we somehow got a quad in there. Like we want to make splits where we don't only divide um, the triangles that we have based on the length, the size, but also the number of triangles there's going to be in each box. And there is this very clever heuristic, and a heuristic is basically sort of a guideline that the algorithm follows. It works like this. We calculate the cost of the split, and that will be the surface area, SA, of the left box times try count left, plus the surface area of the right box times try count right. And what you'll sometimes see is you'll have some straddle factor in there, and that straddle factor is there so you don't get a lot of triangles that are in both boxes. So to give you an example, triangles. Let's see if I can visualize this. Yeah, like so you don't get split. Wow, I'm really not paying attention very well. Like you have a split like this, and then, for example, you would get another box like this. and there's basically a lot of overlap. We don't like overlap. In the perfect world, there would be no overlap. Fortunately, it's not a perfect world, so we usually have some overlap. But if we can minimize it, it's good. And if you want to know like the more theory about the surface area heuristic, there's probably a lot of stuff about that on Google. And you should definitely check that out if you're interested. But I couldn't tell you the exact statistics and mathematics and all of that because I just don't know enough about it really. So let's build this. The cool thing about the surface area heuristic is that we still get a BVH in the same format, same memory layout, but we just build it a bit differently. So we just have to change the code for constructing it. So what I'll first do is add a define split type. I will define the median. And the SAH. And I'll set this to SAH. So that way I can get rid of the parts that we don't care about for the median. So we only check like we only really check a maximum depth if we do the median. We still only split the longest axis if we're doing SAH usually to make it fast. But this split plus like this is if split type is median. Oh, this is split type median. Yeah, that's recognizing it. Let's see. Let's not make it efficient yet. Let's just make it work. So we still do that dry run. Because technically we could get rid of that dry run when we're looking through the SAH. Because we'll be doing a dry run to find the optimal split plane. Or actually, we can do this. It's not that difficult to get it out there. We just need to define some variables here. So we know what variables need to be set. And then we're good. Yeah. Here I'll define how many planes we'll test for splitting. So we'll test 8 different positions and pick the best from that. We can do more, we can do less. Let's start with 8. So we loop through the planes. It's going to be the longest axis length. Delta split. So we calculate the distance between the splits. And one thing that I learned the hard way is if we're going to do these tests for splitting, you don't want to test all the way on the left, and you don't want to test all the way on the right, because it's never going to end up with a good split, and the surface area heuristic will actually think it's a good split. Are you reading up on the SAH? Yeah, it is amazing how great this works. Like, everyone uses this. Everyone is using this for ray tracing, for the BVHs. Well, even outside of ray tracing, for physics, you use a lot of BVHs. Gameplay code too. If you want to like look up like what's the entity next to this entity. So for calculating the delta between the splits, let's see, I'll just 1, 2, 3, 4, 5, 6, 7, 8. It's 1, 2, 3, 4, 5, 6, 7, 8, 9 distances between the splits, so we need to actually divide by 9, or just the split, the plane test count. Plus 1. And the first position is going to be axis lengths 0 plus the delta split. We can calculate that in here and have that times p. Longest axis. And you can also do a surface area heuristic where you test all the axes. I just tend to stick to one for fast construction. I'd rather test more planes on one axis than test fewer planes on multiple axes. Yeah, so we can just run this dry run. Figure out on which side of this split position we put things. We'll do this. Min ABB left, max ABB right. Oh, that's also for left. We should be for right. I'll make this very large. I'll make this very small. We'll calculate the best cost. Wow, the tiredness is definitely kicking in here. So we have the split position. We put them left and right so we can calculate. Oh, we need to update the ABB. I can take this out of the loop since we are calculating this for either left or right. And in this other case, we just update the right ABB. And once we've gone through all the triangles, we have two ABBs and we have two counts, so we can calculate the cost. And that is going to be surface area. I even need to think about how to do the surface area. So it's going to be 2 times, let's see, let's write a function for the surface area since we're calling it twice. So there's 3 planes that we need to calculate the surface area of. First we'll get the size. Um, 2 times size of y plus size of x of size dot z plus size of y times size of z. And that's going to be the surface area. Perfect. And then we can calculate the cost. That's the surface area of the left times the triangle count of the left plus the surface area on the right plus triangle count on the right. And then we'll compare this cost to our best cost. So if it's less than the best cost, then this is our new best cost. And our split loss is going to be this split position. And our try count left is our count left. I actually made a mistake here. Yeah. rather not use uninitialized variables. And then what we should also do is there should be a check. If the cost is greater than the last cost, it means that splitting is more expensive than not splitting, and we should not split. I believe that's how it works. And our last cost is simply, oh well, basically the cost of the parent node. So we can add a surface area. Current elements dot nodes main ABV and the current elements dot nodes max ABV. I will say if the best cost is greater than this node times source area times the current elements dot try counts, that we don't want to split. And if we don't want to split, yeah, we'll pop something up the stack and continue. So it will check if it's a good idea to even split the nodes at all. That's it, I think. Because if we don't find any split plane that yeah, we should always find a split plane. Unless we get some ridiculously high value, in which case we'll decide we don't want to split. Yeah. That should be good. Let's see if this works at all. Did not work. Let's see why. Count right is 0, and it should never be 0. So we even got like a really high number on the right side. What split position did it decide to use? 2.8, and our delta was 0.8. I made the delta split still too large. So what's happening is it's starting here, then goes there. No, it actually still starts at 0, then 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 0, 1, 2, 3, 4, 5, 6, 7. Yeah, I should definitely add a +1 offset. That doesn't explain why everything is on the left side. That would explain why everything would be on the right side. But it should definitely be like this. Because we don't want to check the outer edges. Right is 0 again. Well, let's just step through it, see what happens. So in the first split, everything goes to one side. Oh, I'm doing this whole completely wrong. This shouldn't be axis lengths. This should be the minimum axis that we should be that we need to add. Like that. Let's call this split start. Yeah, that seems to work better. So let's see what these splits look like. Looks like it broke. So this will be very slow. Oh yeah. Haha. So slow it's crashing. I hope that didn't kill the stream. Is the stream still up? So what happened was that we only have one node with all triangles in it, which caused my GPU to hang because it did like intersecting 134K triangles. So we got an infinite cost. That's a pretty expensive split. Oh, I initialized these wrong, did I? The maximum should be really small, the minimum should be really high. Oh, I'm minning these instead of maxing these. Yeah, so we got these insanely high values that broke everything. Yeah, now we got an actual reasonable cost. Let's test this. It's some value, and this is probably going to be higher. Yeah, 13 times this is going to be bigger than that, so it should split. And now we got actually another bug. So we're again at a point where it's only splitting on one side. And it determined that that cost is best. And best cost is none. So that probably means... No, I actually don't know. Why is the cost not a number? Negative not a number. Let's test for NaN values. Like this, that is NaN. Yeah. It's infinite. It's inf cost. I'll put a breakpoint here. So we can see what happens if we get some weird broken value. Also, cost should always be positive. If it's negative, something is wrong. So the surface area on the right is infinite because they didn't have any don't have any triangles on the right side, so we have an invalid ABB. I see. What is the split position? Negative 0.43. So let's add an extra case. if count left is 0 or count right is 0, we'll just continue. No splitting where all triangles are on one side is always a bad plan, bad idea. Let's test this. It's taking a long time to build the BVH, but it's not crashing. There we go. Let's see if this works. Do we have more splits? Yeah. And you can see, I think you can sort of see that the ABVs are different. And our frame time is way better. Wow, that actually made a big difference, I think. Although the frame times have been fairly inconsistent. Let's compare this depth. I'll screenshot this. And let's compare that with the other algorithm where we do median splits. And test if that still works. Now we broke the median split. Huh. Why did that break? Oh, did this? Yeah. We removed our case where we stopped splitting. So what depth were we looking at? Depth 4. Yeah, you can sort of see difference. Like you see this bit sticking out, but it's not here sticking out. You can definitely see this ABV is different. And if I look at it like this, it's like 3 millisecond frame time. And if I go back to the SAH one, takes a lot longer to build with the surface area heuristic, as you can see. But these, like for oral static meshes, we could test like hundreds of planes and then just cache the BVHs. But even doing just 8 tests gives us way better frame time. This is way faster. But just doing a little jiggery pokery test which plane is good with a heuristic. Beautiful. So I want to add a little to do still to this. Add a straddle penalty to the cost of the split. So we one, we don't want to favor, we want to favor splits with little straddle over splits with a lot of straddle. And also I want to add it to do weigh in the cost of a triangle intersection versus AVB intersection. So imagine that an AVB intersection would be like a quarter of the cost of a triangle intersection. We would like to do more splits, but if, for example, triangle intersection is only like a quarter of the performance, quarter of the time of an AVB intersection, we might want to have less splits. We're going to have bigger leaves. How will you handle large polygons? Right now we don't. What you can do is split them. Right now I'm just going to assume there are no large polygons. But it's a good question. You're reading it, you can share them between bounding volumes. Yeah, how that will work, that's actually not that complex, so I can explain it. So what we usually do is if we have this overlap and we draw a box, oh, that's why it's changing my triangles into boxes. Haha. Okay. So for example, we could have two boxes like this, and here we have this overlap. So this is the usual case. If, for example, we had some really large polygon that we want to split, we have like a triangle here, big triangle there, and then a little triangle there. Hold on, I want to draw a better example. Yeah, starting like this, and like this, and like this. Instead of doing a box like that, come on, and a box like that. So this is basically our large polygon case. This is not ideal. So what you would do is, by putting this polygon into two boxes, is you roughly get something like this. Like you literally just split it over two boxes, and you make sure that these two parts touch. So you sort of get a hybrid of a KD tree and a BVH. And this BVH will still be valid. This is also how the splitting works for yeah, with KD trees. With KD trees you always split triangles on the left and the right nodes. You don't to deal with like overlapping. Because you don't store boxes, you just store the split plane. But in our case, we're right now just dealing with that bunny mesh. That bunny mesh doesn't have any large polygons. So I would rather build that when we have meshes that do have them, and then test that. Yeah. Does that mean you would get artifacts because array could miss part of the polygon. Yes, but I think you could solve that um, by just making these boxes slightly larger, so they're still slightly overlapping. In the case of the KD tree, I think you could only miss part of the polygon if you're directly aligned on an axis, which in the real world will never happen, I think. Um, yeah, basically that. But yeah, I think there are artifacts, but you could possibly solve this with some epsilon values. There's also like a common problem in ray tracing is if you have a triangle right here and we have some light source right there, and we want to trace a ray, like with our camera we hit this point and we want to test, is there anything between this light and between this triangle? What ends up happening is that our our ray starts slightly in this polygon, and because of like floating point imprecisions, it would detect that the triangle the ray is coming from is between the ray and the light, so it will be shadowed. So what you would do is just add a little epsilon value so it can't hit it. And these little epsilon tweaks, you'd use these everywhere, just to deal with the floating point position, because you cannot represent all floating point values really. You can only, well, you can't represent all numbers. You can only represent so many values. You only have 32 bits, or 64 bits if you want to use doubles, but that will make your ray tracing far slower. Right, if only we had infinite precision, and with that also infinite performance. That would also be pretty nice. That would make things easy, right? Oh. Someday, yes, someday we'll have infinite precision, infinite performance. With quantum computers, we'll have a quantum coprocessor. Yeah, we could simulate a universe to move into. Well, if we have infinite processing power and infinite precision, we could have a new universe, and in that universe also build a computer that also has a universe, and we could create this infinite recursive universe. We'd also break the laws of thermodynamics. So that might be a little thing that we need to figure out. All right, let's do one more point, and then I'll go to sleep because it's almost 2 p.m. and I'm actually very tired. Yeah, breaking laws of thermodynamics, just a minor hang-up. I really want to get these ray transformations in there, so we can move the model around, and we can make the Stanford pencil we were talking about on another stream. So we can see what the refraction does to the model if it's partially in the water. Yeah, so to explain ray transformation, if we have a beautiful model of one triangle that is like this, like what if, imagine this is our source data, and we put it right there, and we rotate it, and we scale it, we change the polygon, and we have a ray coming in like this, for example. What we can also do is, instead of transforming that polygon, we transform the ray to work on the source data, so it would come in like that. And we can basically translate the calculations we do in this case to give the same result as if we were doing that. And by transforming the ray, instead of a triangle, we don't have to transform all these vertices. Like, what if we have a million vertices? We would need to transform all our model data for every camera. It would be a mess. But with this, we only need to transform one ray. So I guess there's sort of a trade-off there. If you have less vertices than pixels, I guess that's transforming all your model data would be cheaper. But I'm assuming that at some point you'll have more vertices than rays, more vertices than pixels. And we also don't have to transform objects that are not visible. See, I did a mesh plane thing that was a lot like that. That was just far easier and more efficient to transform the model and do slicing into 2D and transform it back. Yeah, exactly. What it also does, which is actually the real reason why we do this trick that I just was thinking of, is our BVH uses axle-line bounding boxes. If we rotate the model, those don't work. Scaling will work. We can scale the BVH, we can move the BVH, we cannot rotate the BVH. And for this, we'll also need to solve a problem that we've actually solved before. Yeah, we'll just stick this in this constant buffer for now, but later on we don't want to do that. Later on we'll have mesh instances and we'll load it all from structured buffers or just regular buffers. But since we have one model, we can cheat a bit. So we'll say model world matrix, and we have a model let's see, it's like an inverse, it's an inverse transpose, but I want to call it the model inverse transpose world matrix. Yeah, let's call it the normal matrix, like we do with the other case. Because for array direction, if we don't scale uniformly, we get the same problem that we got with the normals. And I think it's somewhere on the YouTube archive, so you can watch it back. Probably the first episode on there. Although it might actually also be done in the one-time stream before I recorded things. That episode is lost. My album finished again. Let me load up a new album so I have some more music. Let's get some Slayer going. Yeah, that's better. Cool. So to use these matrices, I'm just going to create a function that's gonna return array and take array and transform it. what do I call it? Origin, position, origin, direction, reciprocal direction. And these need to be the inverse, actually. So we don't want to inverse matrices. Don't want to inverse matrices. Wow, I'm really tired. We don't want to inverse matrices on the GPU because I think it's also very somewhat branchy code. It's really expensive to calculate, and it's a waste to do that per pixel. Let's look up my inverse function. Okay, it's not branches, just a lot of calculations. Yeah, we don't want to do this in our pixel shader. It's a lot of matrices. Times the rate of origin. This one's actually very simple, except for this. Then we need to do this little trick, because you cannot multiply a 3D vector with a 4x4 matrix. And for the direction, we want to pass 0 for the W, because we don't care about translation. But we don't need to transform the roots reciprocal, we can just recalculate it. So we do this, transform the ray. Cool. Now we just add we just calculate the matrices. Which should be easy, since we already have most of them. I should probably split this file into some more files so I don't keep losing track of what is. Need to add these matrices to the other shader and to the what's its face, to the CPU code. Nope, wrong thing I clicked. It's there. Got it. Cool. We can just use this world matrix. Let's do this. And let's just do the most efficient thing. That's just the easiest to write. Don't really care about efficiency of this code. This is just some microseconds. Don't care about this. That should cover our matrices. Let's test if this works with a unit, an identity matrix. Well, first of all, shader doesn't compile because I missed a letter. Building a BVH. Building BVHs is so. This is not even doing that many splits. Okay, so far so good. Seems to work with our identity matrix. Let's start rotating our bunny again. Loading, 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 loading. Yeah, that actually seems to match. That is awesome, it works. I didn't expect it to work first try. So let's move our bunny as well. Bunny position. How do we turn bunny position? Well, there's just some place that we gave it. So there's still one big thing missing from the ray transformation. That is, we output this t value, the distance. That distance is going to be in local space, and we need to convert that to the distance in our final place. Okay, so it's reflecting on the bottom of the water, but our array, like our setup is not made to output this correctly. But that seems to work. Whoa, that made it way slower. So let's move our bunny up to 0.5. And let's also scale it, test that. Yeah, I really don't feel like adding BVH caching yet, but we might have to. Just to deal with the loading times a bit. I want to have this partially in the water. That's going to look so sick. So far, it seems to work great. But it's still above the water. How high is that water plane? Oh, it's -1, so we should do -1.5. And then it should be in the water. Yeah. The rotation speed is based on how fast we render, so that is definitely reflecting. Okay, now for the real test, non-uniform scaling, because um, that's where our inverse transpose matrix really comes in. How do you add color? Color to the ray tracing for the rabbits? What we're going to do, I actually already put this in my to-do list, is calculate the barycenter coordinates of the triangle that we hit, then calculate the UVs, and then sample from the texture. Oh, that seems to break. See, our reflection is wrong. It's like it's scaled the wrong axis. Okay, so there's some debugging work there left. But it does seem to ray trace the whole thing, it's just scaled wrong. Okay, so let's solve that case a bit later. I first want to clean up this test code a bit. So we first handle the test case, and then if we're not doing the test, we do other things. So if this is greater or equal to 0, we do the debugging guide. Perhaps order of transforms. No, it's not order of transforms, because if it's order of transforms, we'd be like seeing stuff rotating or scaling, not from the center of the model, but from like a different position in the world. No, I think it's definitely in that the inverse transpose of things. So here we'll say return white. Actually wrote return white. That's not gonna work. Else return black. We don't even need that else. Return white if we hit. So that gets rid of this debugging stuff. Yeah, the reason why I make my ray PVH intersect return the triangle that it hits is also there to calculate those barycenter coordinates, because we need to know which triangle we need to calculate those on. So it's already one step ahead there. So let's also add the refraction back. Let's end with a nice looking picture. So we'll get rid of these triangles. I don't really care about these anymore. Doing just a couple of triangles really is boring once you've done a mesh. Just call this riffle hits. It's not equal -1. Make it 1. Make it white. Otherwise, we do this. Oh. I've been bitten by a mosquito on my ankle. It's super itchy. I should not touch it. That'll just make it worse. Look at our Beer's law. Let's see if this compiles. No. This should be the refraction rate. This shouldn't be. Oh, this should. Oh, we don't have the reflection ray here. Yeah, perhaps you should build a different shader for that. And also need the view vector and probably also normal then, yeah. Still stupid mosquitoes. Here we get the refraction ray. Okay, that seems to build. We're getting a lot of warnings in our shader. Possibly an uninitialized value. T. Right. Yeah. But I don't care about this cases if T is initialized because we don't use T if it returns false. Constructing BVH. Okay, let's go to the test case. So the reflection is still there, but the refraction is... Oh, it is working. It's just barely in the water. Let's move it a bit more in the water. Swim, bunny, swim. And then we can finally test if the refraction code is working. So I can't really see it. Is the stream still alive with this? Oh, it says it's like 20 FPS instead of the 60. It's not even using that much GPU power, like it's only 6 millisecond frame time. But it looks like it's sort of killing the stream. It looks fine over here. Except that Beer's law is really broken. Because now we need that T value. So, smooth stream, laggy stream. It definitely seems to be messing around with the refraction of the... Like you can actually see it's doing some refractive stuff. But I still don't know if that's correct. It also doesn't seem to really be applying the Fresnel factor. But that might be because our T is broken. Let's get rid of the Beer's law. I'm trying to think also already how we can transform T back. Oh. Yes, now you see mostly reflection. This reflection just looks weird. Really killing the stream. That should be a bit smoother, yeah. So we definitely have a lot more to optimize. That's just 2 rays per pixel, that's nothing. So to calculate the correct t value, we'll calculate the intersection points. I need transformed ray for that. Do I need the intersection point? Math is difficult, man. Transformed refraction ray is transformed ray. I love trans t. This is also transformed. And then we need to convert this. If we hit, we need to convert this into a regular t. So I think we scale the direction by t, transform that, and then dot that against our original ray direction. Yeah, so we basically do this, trans t times trans refer ray the direction. So we get a scaled trans scaled direction, and we convert this using one of these matrices. I think this one. Let's think about that. We use the inverses of these to go one way, so we should use this to go back. This is direction, so we don't care about translation. We do .xyz, but I'm not sure if we do not care about that. Yeah, because t is just a distance. And then we can say t equals dot scaled direction on the original refraction ray dot direction, which is this is normalized, so this gives us the length. And then we can apply Beer's law again. Moment of truth, lag. Oh, oops. That doesn't seem very Beer's law-y to me. Let's play around with the refraction index. Yeah, anything below 1 looks horrible. But this is so broken. This should never happen. Right? Should it? Does anyone know of a liquid with a or anything with a lower refraction index than air? Uh, let's make Beer's Law like super intense. See if it works. Like if we can get any coloring on there. There's a crazy phenomenon where you can get an IOR below 1, but I forget what it is. Yeah, last time we looked into the refraction stuff, there was a special case when you're going from a higher refraction index to a lower one, where you get a total inner reflection, where it's just reflecting. Yeah, these T values are not correct. It's not coloring the refractive part at all. Ooh, that looks weird. The legs are reflected. It's funny that you can see the speed of the program based on the movement of the bunny. Can I give OBS like a higher priority over the GPU or something? So I really don't like that it keeps lagging. Or can I do like both encodings on the CPU? Because the frame rate just drops when I'm doing this. Okay, so we have two bugs. Bug. Non-uniform scaling doesn't work. We have another bug, and that is transforming T back into world space is broken. I'll just put this like that. Something to do with relativity. Like Einstein's law of relativity, where like uh, where things happen based on gravity and based on perception, like if this thing observes that thing versus that thing observes this thing. Yes, that okay. Well, I don't think that we're gonna simulate that. That's a bit complex to simulate. We're not gonna have any black holes in this little renderer. So this is wrong. I'll write this down. Bug. This doesn't work. And we also know that uh, these matrix calculations seem to go wrong. Oh, I've been streaming for, oh, it's really been nearly 3 hours. It's 2:30 a.m. I think that's going to be the end of the stream. We made something cool though today. Good progress. Wondering, what if I run in release mode or debug optimized? How much faster is it gonna load the BVH? You mad computer scientist? I'm a mad computer scientist. Not even really a computer scientist, more of an engineer. Although I have a Bachelor of Science, technically. So technically, I'm a scientist. Yeah, it looks pretty cool. But the refraction Beer's law stuff is going horribly wrong. Reflection looks nice though. Starting to take shape. Alright, that's where I'll end the stream. Until next time, I won't be streaming next week because I'll be not home. I'll be on a holiday, little holiday. So perhaps a week after I'll find an evening to stream. See you then.